Hello and welcome to Physics 101 with me, Paul Carey, and Cody Cup.
Hello.
Today we will be talking about wavelengths. Wavelengths are just AM, FM waves, whatever you prefer. Today I will be a FM wave. I'll have a frequency of 1000 megahertz. I will be traveling from Earth to the moon and back in part B of our problem. But as you can see, I'm not a wavelength, but today I will be. So for all situations, I'm wavelength. Good, I'm glad we got that out of the bag. So now, I will be starting in the United States. I'm drawing in the United States, the moon. So for me to get to Earth, to the moon, first I need a speed. Well, all waves travel at 3 times 10 to the 8th meters per second. For the people who don't know that, 3 times 10 to the 8th meters per second is the speed of light. So, traveling from Earth to the moon, I will be going at the speed of light. Our known distance on average day is 250,000 miles. 250,000 miles converts into meters to 40,233,600 meters.
Lots of meters.
Lots of meters. That'd be a lot of sticks, Cody. That'd be a lot of trees. So now, if I wanted to go from Earth to the moon and calculate my time, I have to plug it in to our handy-dandy formula, which I already have written down. 40,233,600 divided by our known speed of 3.8 times, or 3 times 10 to the 8th. You do some dividing on your calculators. I would recommend a TI-86 Texas Instrument. They have a lovely conversion factor. And our answer is 1.34112 seconds. So in about a second and a half, I could be to the moon, picking up Earth rocks, chucking them at people.
There were people on the moon.
If there were people on the moon. Now, part B of our problem. See, this is part A. Here's part B. Part C will be over here. Part B of our problem is, what if I wanted to go there and back? What if I wanted to go there, pick up a moon rock, come back, and then chuck it on a person on Earth? Well then, here's the equation. You just take your distance from Earth to the moon and double it, because you're going to go there and back, which is 80,467,200, divided by our time, or not our time, but our speed. Our speed didn't change from the first one, and you get 2.68224 seconds. So in a little under 3 seconds, I could be to the moon and back with a space rock in my hand, and I can throw it at someone on Earth. It's a win-win. But sadly, I am not a radio wave. I'm too big to be a radio wave. I couldn't fit in the radio wave suit.
Still cute though.
Oh, thanks, Cody. So nice. Now, part C of our problem. We are going to calculate the wavelength, which is what would be the length of our wave if it were to travel from Earth to the moon. And kids, I would recommend writing this down. It's a circle. Cut it in half, then cut the bottom portion in half. It's V, which is your velocity, over frequency, and wavelength. Now, wavelength usually isn't WL. It's usually like a weird looking thing, kind of like that. Cody, zoom in on that, please. It's kind of weird, but that's what a wavelength symbol looks like. It's kind of messed up, but I do my best.
It's like a goldfish.
It's like goldfish. Good thinking. Put a little
Goldfish.
tail on it. Give it an eye. And it's swimming into my mouth. Yeah. Anywho, we know our velocity is 3 times 10 to the 8th meters per second. And we know our frequency is 1000 megahertz. But I can't just use 1000. The M in megahertz is mega for a reason. It is 1000 with 6 more zeros.
That's a billion, Paul.
That is a billion. Thank you, Cody. Now, if you take 3.8 meters per 3 times 10 to the 8th meters per second divided by 1 million hertz it gives you. .3 meters. So our wavelength is 0.3 meters long. Now, if there are any questions, you can email us at www.mrfracassa.com. His website is very nice and fun. And that is it for today, folks. Thank you for visiting us with Physics 101 Waves. I am Paul.
And I'm Cody.
You have a nice day.